Okay, you should have heard something that said this meeting is being recorded. I apparently don't hear that on my end because I'm the one that tells it to record. Anyhow, here we are. It's being recorded, and that recording, when Zoom, I want to say WebAssign, when Zoom gets around to processing the video from today's class, it'll be posted. Now, what I was saying was that you want to approach the WebAssign homework by reading the text, reviewing the videos from class if you find that helpful, um, looking at other videos, other sources, look at systems of linear equations. Google that and find something that you find helpful. Get all that done before you start the problems. Don't dive into the problems and just do whatever's necessary to get the answer right. Do it by the process that builds understanding so that you'll have that understanding when you get to the test. Because again, their tests are at least 75 or 80% of the grade in this course. The other thing is that there'll be basically 2 tests. That we might decide to do 3, but I think 2, basically a midterm and a final. I'll also assign written work, handwritten work. And that handwritten work, you're going to need to, I'm assuming everybody has a smartphone. If anybody doesn't, let me know. There are alternatives, but the easiest way to get the homework to me is using the smartphone and an app that allows you to just take pictures and converts them into PDFs. And I really want PDFs if possible. Reason I need PDFs is that people will sometimes write too small for me to see it. And I can only enlarge stuff so much. And actually with the software I prefer to use, that allows me to click through it rather quickly so I don't waste a lot of time clicking around. I can't even enlarge it, but if I've got PDFs, I can. Any written work is going to need to be legible. And that's pretty much it. And you're going to email that. And you're going to email that through your VHCC account, not through Canvas. Sometimes it doesn't make any difference, but Canvas is managing not to impress me very well for various reasons. If I send you an email, I don't get a copy. So if I want to see what I sent you, I've got to go back through all the emails that aren't there in very good form. They're not very searchable, and try to find it. Yeah. So I usually don't send emails through Canvas, except maybe these Zoom links and stuff. And emails that I get through Canvas don't have all the features of VHCC email, making it kind of inconvenient to use. So again, use your VHCC email when you're sending me written work, and there will typically be written work due. Let me see how I've got the assignment set up again. Something weird about that. I got one date that I'll need to change, but that's not going to be a problem. Okay, so typically there'll be written work, and you're going to need to get that to me so I can actually see how you're constructing solutions. Doing mathematics is not a matter of clicking on answers or typing in short answers. it comes out to creating a solution and expressing it in a sensible manner. Okay, well, that's enough about that. Okay, that's some general things about the course. Let's go ahead and look at the first topic. Now, this is something you should be very familiar with. I keep going back to my high school education, which was just a good solid high school education. It wasn't a prep school type education, but it was in the first half of the 1960s, which you know that kind of dates me. I'm approaching middle age, so uh, it was during the space race, at a time when science and technology was emphasized much more than it is now. Now we've got STEM. Nobody said STEM then, just you learn this, okay? And everybody did. Everybody that was in college preparatory courses uh, learned how to solve systems of simultaneous equations, okay, using Kramer's rule uh, or using substitution or using elimination. Um, so these are things that I kind of expect people know, but I get surprised a lot of times and find that people don't. And that includes people like you who are very bright and have the appropriate or a decent background in these courses. So I'm not sure why these things are falling through the cracks. Uh, so I'm going to kind of do this in a basic manner. And I say all that because if I'm getting a little too elementary for you, I apologize. But I want to do this in a way that makes everything clear. So what do I mean by a set of simultaneous equations? Well, what we're dealing with in this course is simultaneous linear equations. So I've got to see where the board is. I've got a weird angle with the camera here, but this angle allows you to see what I'm writing without me blocking it too much. So we're going to use this angle here and maybe adjust it a little later. Okay, so simultaneous linear equations. This board is a little floppy. So my writing's even a little worse than usual here, but it'll improve. Okay, simultaneous linear equations. Okay, simple example. Okay, right there's a simple example of linear equation. Now, there are two ways you could solve this system. There's more than two ways. I'll show you another way in a minute. One way is to, let's say, solve the first equation for x or y. Let's say we solve it for y. Now, it should be clear that if we solve this for y, we're going to subtract 3x from both sides to get 8 minus 3x. Then we're going to divide by 5. We'll have 8 minus 3x over 5. Then we plug that in for y down here, and then simplify this equation. We're going to get an equation that just has x's because the expression for y is in terms of x. So when we substitute that expression here, this term of the equation will be now an expression in x. So we just have x's and we can solve it just like we solve any linear equation, very easy to solve. Okay, well, that's great, but we're not going to do that in this course because this course is confined to linear equations because it's a linear algebra course. We use the method of elimination, okay? So we solve by elimination. Okay, now we want to eliminate one of the variables. Okay, well, I can eliminate a variable. If I multiply this equation by 5, by 3, and this one by 5, what's going to happen to my y's? If I multiply this one by 3, I'm going to get 15y. If I multiply this one by 5, I'm going to have a minus 15y down here. And then when I add the two equations, the y's go away and I have an equation in x, which I can solve very easily. Okay, so I'm going to use a notation that I usually use. 5 times a circled 1 means I multiply the first equation by 5. And it's clear that when I do that, I get 15. Not going to multiply it by 5. Y'all are trying to confuse me. Okay. And no, it wasn't you that did that, was it? We multiply the first equation by 3, and we don't get 15. We get 9. Now, I'll warn you. You got to keep an eye on me. When I do stuff like that, it would be great if somebody out there would volunteer to unmute their microphone and just scream, okay? Before I go on with the error. Anyhow, I got 9x plus 15y equals 24. Because of course, as you know, if I multiply the left-hand side and the right-hand side by the same number, I don't change the solutions to the equation. Okay, then I'm going to multiply 5 by the second equation. And that's going to give me 5 times 2 is 10, so I'm going to have 10x. Then we're going to have minus 15y, and that's going to equal negative 5. Okay? So now I add my first equation to my second equation. The y's are going to go away. And I get 19x equals 19. Now I set this equation up so it's very easy to solve. Okay. So obviously then I could get really elementary and write out all the steps of the algebra, but this will be sufficient. And I get x equals 1. Now what do? Well, I substitute x equals 1 into either of my two equations. So, and I'm going to do that with some arrows. I'm going to substitute this into, well, the arrows work best for the second equation. So this goes into here and gives us what? Gives us 2 times 1 minus 3y equals negative 1. Okay. And I'm going to write that up here. One thing that I realized after doing a video in Zoom, and I just started doing that, I just experimented with all kinds of things to see if this would work. There's some disadvantages to that. One is there's this logo that goes across the screen right about here. Okay, so you're not going to be able to see that. So I'm going to write it up here. So I get 2 times 1 minus 3y equals negative 1. And that means I have then 2 minus 3y equals negative 1. So that y equals negative 3y equals negative 3, and y equals 1. Okay. Now there's my solution. If I substitute this and this into, let's say, the first equation, because I don't want to substitute them into the second equation since I used the second equation to get this equation. So if I had a wrong solution for x and plugged it in here and then did this step right, my solution for y would agree with this equation. But if there's an error at this point, it would not agree with the first equation. So we substitute these values into the first equation, and yeah, that's right. Okay, saw something there, didn't look right, but it was okay. Okay, so I substitute these into the first equation. I'm going to say we substitute those into the first original equation. And I get 3 times 1 plus 5 times 1 equals 8, which tells me that 8 equals 8, and this checks. And this doesn't tell us for sure that the solution is correct, and we might have made a mistake, but it's extremely likely. Okay, you probably have 95% or better likelihood that you have it right. If you then substitute into the second equation, that goes up to probably 99%. It'd be a very big coincidence if you made errors in substituting into the first equation and into the second equation that misled you into thinking that you had a correct solution. Okay, so probably okay. Well, that's good. Now there's another way of seeing the solution to the equation, to the system, and this is very important. The geometry of these solutions. As you'll see later on in the course, when you try to visualize what these solutions are telling you. Okay, so I'm going to move this board over just a little so we have a better camera angle. Can't move too far because I've got furniture in the way over here. But I'm going to take the two equations, which we can still just barely see on the screen, and I'm going to graph them. Now, I'm not going to go over the details of how you graph a linear equation. There are various ways to do it. So I'm going to just sketch a set of coordinate axes. And 3x plus 5y equals 8. The x-intercept is going to occur when y is 0, of course. So if y is 0, you get 3x equals 8, so x is 8/3. And the y-intercept, if x is 0, you get the y-intercept is going to be 8/5. So those numbers are both less than 1, less than 2. Their absolute values are less than 2. And if I look at the intercepts here, they're both less than 1. Absolute values are both less than 1. So I'm going to use a scale where 2 is here and -2 is here. And then up here, it's going to be a little distorted because this 2 is smaller than this 2. But now I can sketch the intercepts. The y-intercept is 8/3. That's actually more than 2. That's 2 2/3. Okay, so I wasn't thinking clearly when I said it was less than 2. But okay, I'm going to say that, well, 2's here, so 3 would be here. 8/3 is 1/3 less. So this is 0 8/3. And then we have 8/5, which is 1 3/5 or 1.6, a little more than 1.5. So I'm going to say, okay, this is the point 8/5, 0. Then my intercepts here, if x is 0, y is 1/3. So we have 0 1/3 here. And then if x is 0, if y is 0, x is -1/2. So we're going to have point -1/2, 0 here. And now I can sketch my lines. Okay, this line is here. And the line through these points is here. And that worked out much better than I could ever expect from a hand-drawn graph, even though I was pretty careful. The point where these lines intersect has what coordinates? Well, if I do an honest estimate, I get something like 0.97. And this one just happened to come out right at 1. Okay. And we suspect that might be close to 1, which of course agrees with the solution to the equation. Okay, so we have a graphical solution. Now your graphical solution is not going to be exact, and you want to do your graphical solution by hand. You don't want to shortcut it by using software. Sketch the blame thing, because that causes you to think about it in a different way. Okay, I certainly know how to use software to graph a couple of linear equations, or calculate or whatever. Sketch it by hand to reinforce the ideas you're going to need to have access to in the future, especially like on tests, but elsewhere as well. Okay, so that's it. Now, one reason that the graphical idea is so important is that there's a graphical picture of different things that can happen when you get two equations. Okay, well, what I mean is there's no reason that your two equations can't give you parallel lines. Okay, so first time you send me right out of room to write a word, you'll see that a lot. But it says lines can be parallel and non-intersecting. Okay, so there's no solution. Since the lines don't intersect, there's no solution. If there's a point where the lines intersect, you're going to get a solution out of this. Okay, now we'll illustrate that in a minute. We're going to, I think, have plenty of time to do that. Okay, lines can be parallel and non-intersecting, or and I'm going to use two different colors here. And those lines are really close together. The two different colors, yellow and purple. Not sure how well you can see that on your screen. Okay. Or parallel and intersecting. And in that case, here you get no solution. And here you get infinite number of solutions. Okay. Might not be able to read that. Infinite number of solutions. And I say every point on the line, I don't have room to write on the line, but every point on the line is a solution. Now, did I get that? Solution. See if I can read that on my screen. Oh yeah, if you just to make sure we see it, I'll lift up this end of the board a little bit. Okay, every point on the line is a solution. Okay, well, that's a good bit of what you need to understand about a system of two simultaneous equations in two unknowns. I'll quickly illustrate both of those ideas. It's still a little damp. Let's see if that's going to work. It's about 42 degrees in this room. This is in a cave in my basement. It's not really a cave. Got a walkout basement. It gets a little chilly down here. And, you know, I had this heater on, turned it off because it's kind of close to the microphone I'm not using. Hopefully this background sound isn't picked up that well by the camera. Can you tell a difference in the sound when I have this on? Give me a yes or no. Even a Y or an N would be sufficient. Got one no. Don't need everybody to go along with it. Okay, you're not seeing any difference in the sound. Okay. And this board is a little damp. It's not going to show up as well. And that one still has writing on it. That was ignorant. Let's try this one. Yeah, that one's pretty dry. At least they're not frozen. Fingers feel a little cold, but no big deal. Okay, example. Okay. There's two equations. If we want to solve them, well, we multiply the first equation by 7, let's say. We get 14x plus 28y equals 84. We multiply the second equation by 2, and we get negative 14x minus 28y equals 16. When we add the two equations, we get 0 on this side because the 14 and the negative 14 give us 0, the 20 and the negative 28. So we get 0 equals 100. This ain't so ever. For any set of x, y values. So there's no solution. Okay. And these lines are parallel. Okay. If you put them in slope-intercept form, you're going to get a slope of 1/2 for both of them. And you can check that out. lines are parallel and they're not intersecting. Okay. Now there's another possibility. Example here. Let's just take the same numbers here. If I did that right, and let me just check it out. Yeah, that's going to work. Okay. The first equation multiplied by 7 gives me 14x plus 28y, and then 7 times 12 is 84. Okay, it's the same equation we started with here. The second equation is again going to be multiplied by 2 because that's going to match up the x's. It also turns out it matches up the y's. It minus 14x minus 28y equals negative 42 times 2 is negative 84. If you add them, you get 0 equals 0. And this is true for any xy pair that satisfies either equation. Okay. So solution of one equation is a solution to the other. Points on the lines are identical. In other words, you get the same line. And there are infinitely many points, so there are infinitely many solutions. Infinitely many points on the common line implies infinitely many solutions. Okay. So now, I'm not sure I want to get into talking about free variables and bound variables. Let me think a minute. Look at the time. Don't talk about it today. We'll talk about it next time. Yeah, that's good. I want to give that a little more time than I have today. Okay. So there you have the situation. Now this is for simultaneous equations, 2 equations in 2 unknowns. We can graph these things in the plane. Okay, well, you could also do 3 simultaneous equations in 3 unknowns. And of course, you can do 3 simultaneous equations in 2 unknowns or 2 simultaneous equations in 3 unknowns. And those are important ideas. And you'll see some of that in the assignment. Here's another example then. And I'm not going to work this example out in detail for reasons of time, but it's a simple enough process. Let's just start with the same 2x plus 4y plus 7z equals 18, just making up numbers. And now different numbers here. Okay. Now this is two equations in three unknowns. I could eliminate x or y or z, but then I would still end up with an equation in both x and y. Or both, yeah, okay, if I eliminate x, then I'd still have y and z, and I'd have no way of eliminating them. I guess this is worth doing. Okay. Each equation is represented by a plane in R3, R3 being three-dimensional real space. For example, the first equation passes through the points what? Well, what I'm going to do is I want to find the x-intercept of this point. Now you have x, you have y, and you have z. Okay, well, if I let y and z equal 0, I find the x-intercept. And clearly, if y and z go away, I end up with 2x equals 18, x equals 9. Now, if x and z are both 0, I get 4y equals 18, so that y is 18 fourths, which reduces to 9 halves. So I get 0, 9 halves, 0. And then if I let x and y equal 0, 7z equals 18, z would equal 18 sevenths. I can even sketch a picture of that. I'm not giving myself a lot of room here, but let's see if I can get it on there. Okay. X-intercept is 9, and I'm going to have to kind of raise this part of the board a little bit so you can see it. Okay, so you'd have the point 900, y, here is z, here, x here. Y would be 9 halves, the y-intercept would be 9 halves, so this would be 0, 9 halves, 0. And then you'd have 0, 0, 18 sevenths. And I'm just going to draw an arrow from here, meaning you can kind of visualize this plane by sketching this triangle. Okay, so this triangle from the x-intercept here to the y-intercept here to the z-intercept here is part of the plane. And now you can see that the plane kind of looks like this. Well, you could do the same thing for this and get some idea of where the intersection is. Now I haven't left myself a lot of room. and I want to keep this here. Okay, so if I do this plane, it's going to be at a different angle. And two planes in space, as I hope you understand, intersect in a line. Okay, so we get two intersecting planes. The intersection's a line in R3. I can even give you the equation of that intersection. Let's see, what's the easiest variable to eliminate here? I guess it would be z if I can multiply all these numbers by 7. And I'm going to do that in my head. Okay, so 7 times the first equation plus the second equation gives us, okay, that's going to be 14 and 5 is 19. 19x. And then and that's wrong. Should be 7 times the second equation added to the first. I should think before I write, but it doesn't always happen. Okay, so if I do the first plus 7 times the second, what I get is I get the 2 here, and 7 times 5 is 35, so that should give me 37x. And then 7 times -3 is -21, add that to 4, I get -17y equals 7 times -6 is -42, add that to 18, and we get 24. -24. So did my arithmetic, there it is. Now there's more to it. And I don't want to write out the rest of it. This is a line in the XY plane. If you take any point on that line and plug it into one of these equations, you're going to find a z coordinate, and that's going to be the z coordinate of the point on this line. And I don't want to get into those details. I'm not assuming everybody's had multivariable calculus at this point. I don't think most of you would have had it, because I think most of you probably had a calculus course in the fall and not a multivariable course. So yeah, that gets a little into what we do in multivariable. Fairly simple, but not something I want to lay on you now. Just giving you the geometric picture. Okay, I'm going to run over to 10:30 just a little since we got started a little bit late. But that's an example. Again, intuitively, this is a plane. You can kind of visualize it here. You do the same thing with this one and visualize that plane, and maybe even visualize the line where the two planes intersect. If you have 3 equations and 3 unknowns, you can eliminate two of the variables. Okay, you can eliminate, well, I can say it, but I kind of need to show you. Okay, this board's probably dry enough to use. Now, I want to go ahead and use the same equations that I did, but I'm going to add a third equation. Then we get 18. And then we have 5, -3, -1. And that was -6. And I'm going to fudge a little bit. By saying z equals 5. This way I can use what I did previously. And of course I've hidden it from myself, so let me put it out here where I can see it. Put it up here where you can see it too. You want to see everything. Okay. Again, equation 1 plus 7 times equation 2, if I did it correctly, gives us this. And then the third equation is still again, writing before I think, just arbitrarily picked one of these. I'm going to change this a little bit. Don't want that. Don't want that. I want the third equation to be simple, but that was a little too simple. It didn't fit with what I did before because I didn't think it through. Okay, so let's say it was 5y equals 8. Okay, now the third equation multiplied by 1/5 tells me that y equals 8/5. Bad looking 8, but I think you can read it. Okay. Okay, now if y equals 8/5 and 3x minus 7y equals 24, well, now we can substitute this in here, and that gives us 37x minus 17 times 8/5 equals -24. And nobody in their right mind deals with fractions when they don't have to. So if I multiply through this equation by 5, I'm going to eliminate that denominator. And I'm going to have what, 185x minus 8 times 17 is 126. And this is going to be -120. 185x equals 6. So x equals 6 over 185. Now I know that y'all pretty good. And glad somebody is, because I can't see that. Can you? Let's see, we got the 185x equals 6, but I'm not sure you can even see that when Zoom does its thing. So let's make sure we get down here. But okay, we get x equals, and it's not 185 over 6, it's 6 over 185. Now we can take this and plug it in to this equation. No, we don't want to do that. We've got y and we've got x. So we can take the y and the x and plug it into any of the original equations. We don't want to plug it into this equation because this is the equation we used to get this. Think about that. So drawing a couple of yellow arrows. How am I going to get from here to there? Okay, I'm going to take this and plug it in here. I'm going to take this and plug it in here. And what do I get out of that? I get 5 times 6 over 185 minus 3 times 8/5 minus z equals -6. Things get a little crowded there, but I think you can read that. Well, now z is the only unknown we have. And all I have to do now is multiply the numerator and denominator by 5 times 185. That'd be 925. Get that right. So multiply everything by 925, and I get an equation I can solve for z. So z equals something. And now we have x, y, and z, and you can work out what z is. That's a point in three-dimensional space. We know that x is going to be 6 over 185, y is going to be 8/5, and z is going to be this. And let me just do a quick estimate. 30 times 900, 2,700, and 24. Oh man, that's going to be a mess. It's not 2,700, it's 27,000. And that's going to be 24, about 2,000. It's going to be 27,000 minus 2,000, 25,000. It doesn't make any sense. Oh, it's got to be 925. So 925 into 25,000 is going to give us about 27. Can't be. Yeah, I don't want to think that hard. I'm getting an answer that doesn't seem like it's going to be right. But the point is, you're going to get a point in three-dimensional space. Now, just like with lines, two planes can be parallel and non-intersecting, in which case there's no solution. Okay. They can be parallel and intersecting, in which case every point in the plane is a solution. You have infinitely many points, infinitely many solutions. Or they can be intersecting. There are no other possibilities. You can think it through. Take a couple of pieces of cardboard and make planes out of them and see how they intersect, or they're parallel, or they could coincide. There's no other choice. So there's simultaneous equations and some geometric parallels. And that should give you sufficient information, introduction. And I'm sure that some of you, and maybe all of you, might pretty much know all that to start with. So if so, I apologize for boring you. That's kind of it. Okay. Well, good luck on the homework. And I'll see you next time. I'm going to stop the recording.